16, we really just know already because of switching forms into exponential form. So anytime you take the log of 1, we know that the answer is always going to be 0, because anything to the 0 power, when I switch it into exponential form, gives me 1. So I already know that that's a fact, but that's actually defined as a property of logs because it always gives you your x-intercept. We also know that anytime the base matches the number inside, the power has to be what? No matter if it's log base 2 of 2, log base 7 of 7, what's it always going to equal? 1, right? Because the base raised to the first power will get me back to itself. Having a pen malfunction. Let me try pencil. All right, the next one. Raising something in a power inside a log, right? If it's already the same base as the number inside, the answer must be y, because the base raised up to that power is what's going to give you b to the y power. And then the last one is a little bit harder. We skipped over this idea when we were talking about 315, but basically an inverse undoes itself. And so if your base matches the base of the log up in the exponent, things cancel out and you just are left with x. So I can prove that to you, but I'm just going to write because inverses undo. So you don't have to prove this. I'll show you why it works. So you don't have to write this down. But if I have b to the log base b of x equals question mark, right? I want to know what this evaluates to. I'm not going to use x because I already have x in this problem. So what does this evaluate to? If you're stuck in exponential world, you're going to rewrite your problem using a log. So how could I rewrite this expression using the log formula? The base of the exponent would become the base of my log. The question mark is what I'm now taking the log of, and the exponent moves outside. So using the one-to-one property, do you see how the question mark has to be equal to x, right? I just proved it. This base becomes the base of the log, and then the question mark and the exponent change positions, so x has to be equal to the question mark. So when you've got an exponential expression with a log in the exponent and the bases are the same, they cancel to give you x. We're not going to see that a whole lot, but it's an inverse property of logs. So all of these should kind of be proven just by changing into exponential form. So there's nothing there that you have to really memorize. You should be able to evaluate the log of 1 just by changing it into exponential form. Here's kind of the new properties that we're going to need when we start simplifying log expressions. All of these properties come from their exponential inverse. So before I talk about log properties, we should remember our exponent properties. When I had x to the 7th, x to the 5th, what property did I use? I added my exponents together, right? It was called the product property for exponents. Well, guess what? The product property of logs is basically the inverse of this property. So here I added my exponents together. The log product property allows you to take a product inside a log and split it up into 2 separate logs. So the log base b of r plus the log base b of s. So it's kind of like addition gives you the multiplication problem. Over here, the multiplication gave you the addition problem. So whenever you have a product, think addition. How can I split this log up into 2 other logs? The base stays the same, and I can change it to 2 logs that are being added together. So I can rewrite log base 6 of 21 as the log base 6 of 3 plus the log base 6 of 7. Log base 6 of 3 plus the log base 6 of 7. Not very useful right there, but there might be other times when you're allowed to evaluate because of this property. So I'm thinking of like maybe this problem. What if you had the log base, I guess it doesn't really matter this way. I was trying to think of one that you wouldn't know, but you know once you multiply them together. I can't think of one off the top of my head. Log base 2 of, yeah, I guess this doesn't really matter. You could do this one without needing this property, but instead of having to evaluate the log base 2 of a half plus the log base 2 of 16, I can bring these together and make this the log base 2 of 8, 1/2 times 16. So then I'm just evaluating that one log, and I'm getting that the answer is 3 in one step, instead of having to evaluate this log and then evaluate this log separately. This came into play. Remember I said that before they had graphing calculators that could evaluate logs, you might not have the log of 27 in your table. Your table might only have the log base 6 of 3 in it, or the log base 6 of 7 in it. So you could grab these separate logs and figure out adding them together is the log of 21 or whatever it is, like 3 times 7. Okay, so quotient goes along with our, if you have x to the 7th over x to the 5th, you know that you can subtract the 7 minus the 5. It's kind of the same here. If you're dividing inside a log, you can split it up into a subtraction problem of 2 logs. So the log base b of r minus the log base b of s. So I don't know the log of 2/3 anyway, but I'm allowed to take the log base 4 of 2 by itself and subtract log base 4 of 3 by itself. So those are equivalent statements. It might help us when we're solving or simplifying logs later. Right now, we're just learning the property for the sake of the property. Here's the most useful one. The power property allows you to get rid of a power inside a log by bringing it down as a coefficient inside the log. So if R has a power, I can bring the power down and use that as a coefficient, so I can just evaluate the log by itself. So it makes this next problem easier to evaluate. I don't know 36 squared, but I'm allowed to take 2 as the coefficient and then just evaluate the log base 6 of 36. And I know the log base 6 of 36. How much is the log base 6 of 36? 2. So the answer is just 2 times 2. So I can get 4 without needing a calculator. I don't need to know that 36 squared is, what's 36 squared? 1,296. I never needed to know that number. This is a pretty easy one to evaluate using that property. So to me, these are the 3 new ones that are going to take some practice to memorize those properties, but the idea is we're going to simplify logs using these properties. And then we already talked about the change of base formula. When you don't know how to change the base on your calculator, you can take the common log of x and divide by the common log of the base to get your answer. So I can take the common log of 9 and divide by the common log of 6. Or I could do the change of base formula on my calculator. So I'd like you to take a minute, see if you can figure out if these statements are true or false using properties of logs. So see if they obey the property up above or if they disobey the property and they're not actually true. So I'll give you a minute to try them. Take a guess if they're true. It should have been, if I was going to make this true, this initially should have been written x times 2 inside that log, and then I could have split it up as natural log of x plus the natural log of 2. You are not allowed to split up an addition binomial. It does not work. It doesn't equal that. So this one was false. These are both true, right? Because I can take this power, bring it down front, and then I've got 3 times the log base b of itself. This is equal to 1, so 3 times 1 is 3. So this was true. And then this one is also true. You can prove it either using the power rule, so you could bring it down front, and you've got 2 log base 5 of x, which is log base 5 of x plus log base 5 of x. Or you could think of it as x times x in the parentheses, right? This is why the power rule works. X squared is x times x, and I'm allowed to split that up as 2 separate logs, log base 5 of x, log base 5 of x. So the power rule comes directly from the product property. That's what you would use to prove that the power rule works. So that was also true. All right, so on the back is going to feel like, why do I need to know these properties just for the sake of knowing the property? So today we're just studying the properties, but we're going to use them to evaluate and simplify once we have the properties down pat. So there's really no use in ever moving between these two forms just for the sake of moving between the forms, but this is just to practice the properties. So 4, 5, 6, and 7 each have an equivalent statement on the right, A, B, C, or D. So you need to use the property. So for example, number 4, if I'm adding two logs together, what am I allowed to do? I'm allowed to multiply the stuff inside, right? So if I take 4 and multiply by 3, don't I have the log of 12 as its equivalent? So see if you can use the property and come up with their equivalent match on the other side of the column. And then I'll show you how to do 8 through 13. So you're using the property to match it up. So what would the next one have to be? The subtraction one. Yeah, it has to take the 3 and divide by the 4. So that one has to be the log of 3/4. These all are common logs, but the base has to be the same for the property to work, right? If you have a log base 2 and a log base 5, you cannot combine them because they're not like the same log. All right, and then 6 and 7 are both going to be that power property. You can take the 3 and make this a 4 cubed, and you can take the 4 and make it a 3 to the 4th power. So number 6, 4 cubed is 64. So 6 should have gone with C. And 3 to the 4th power is 81. So 7 should have gone with B. So could you match up? I'm not going to ask you a lot of property questions on your test next week, but there might be a question where you have to say what is an equivalent statement. All right, number 8 through 13, this is old school log properties. This is when you had to look it up on a table. So the log of 5, all they want you to do is use A and B to represent your answers. So the log of 5, we're just calling B. They're telling you that log of 5 and B are equivalent. So how can I use A and B to represent the log of 15? 15 is 3 times 5, right? So I really have the log of 3 times 5 as the log of 15. And what am I allowed to do? I can split it up as the log of 3 plus the log of 5. Well, what's the log of 3? Log of 3 is A, and the log of 5 would be B. So this seems really abstract and pointless, but I can take the log of 15 and represent it as A plus B from above. Does that kind of make sense? You're taking the product of, or the factors of the number, and then if you're adding them together, you're adding A plus B. If you're subtracting them and dividing them, you might be subtracting A minus B. You might be using 3. You might be using an A, and a B. So you'll have 3 terms at the end. So like the log of 9, how can I represent the log of 9? Using the number 3 and the number 5. 9 is what? 3 times 3, right? So if I can rewrite this as the log of 3 times 3, how can I now split that up using my just a log of 3? It would be the log of 3 plus the log of 3 separately, right? So that would be A plus A. Or if you wanted to leave your answer as 2A, that would also be correct. So it's kind of like a puzzle just to practice your properties. And so I'd like you to try 11, 12, and actually, you know what? We can pause on 11, 12, and 13 because we're out at 9:08. I just want to show you 14 and 22. And then we can start with this next time on our early release day. If I have 5x and they want me to expand it into more than one log, I could take the log base 4 of 5 and add the log base 4 of x. So multiplication becomes addition. You might have some subtraction problems because of this fraction. And then if it says condense the expression, if you've got addition, you're going to change it to a multiplication problem. So it's going to be the log base 7 of just 12. So now I have one log that means the same as the two logs did. So I'm going to stop there on your notes so that we can